Good morning. Today we are going to see about flexible link kinematics. So far we have seen rigid robotic kinematics. So first time we are going to see in our lecture flexible link kinematics. The organization of today's lecture will be as follows. First we have the introduction, followed by kinematic modeling of flexible link, and then we see an example, that is basically two link planar flexible manipulator, and we just list out the various boundary conditions how the links will be connected either in its base also to its end, how the flexible link is connected in its base as well as in its end, either it is fixed, pinned, here also fixed or pinned, or it is free. So, these are the boundary various conditions we are going to see, just the name of those conditions, and in that only one condition we are going to see, because the rest of the other conditions we will be seeing in the next lecture, and finally conclusions will be drawn. I repeat the organization again. First we see the introduction, then we have the kinematic modeling of flexible link, we go up to the differential kinematics. So, in the kinematic modeling we go up to differential kinematics, that is forward kinematics, then we go to the Jacobian matrix, and then we have an example, that is basically two link planar flexible manipulator, and then the various boundary conditions will be listed in this lecture, and in that only one condition we are going to see. Finally, conclusions will be drawn from the lecture today. Coming to the introduction part. So, coming to the flexible link. So, flexible link, how it gets a shape. So, for example, if this is the base frame x naught y naught. So, flexible link will have the shape like this. So, here you have the point mass, and here this is link 1 and link 2. This is a base frame, and we have the system in such a way that the link L1 is a flexible link, link L2 is a flexible link, and they are connected in such a way that pinned, that is basically the first link is pinned, and the second link also, if you see that the first link's end is also pinned, and this is for link 1, and for link 2 it is pinned, and then finally pinned free, because here it is pinned, and here it is pinned free, because this is a free end here. So, this is for link 2. So, this is how it becomes, and there are variables which are joint angle in the case of rigidity, and that is another thing is called deflection. We can say del I, precisely we can say Wi, which is a function of xi, where xi is a point along the flexible link, that is called xi. So, this is the deflection of the flexible link, and we know that the rigidity based on joint angle theta. So, we know that because of rigid robot kinematics and dynamics, we know what is theta I, which is the generalized coordinate for the robotic system for rigid links, and the deflection in the flexible link will be given by the term Wi of xi. That is the one which determines the deflection of the link Li having the flexibility. And coming to the modeling, kinematic modeling of the flexible link, we are going to see first the kinematic modeling of the flexible link. So, first we consider the schematic, which is given precisely by this diagram, which is basically x naught, y naught, and this is the flexible link which is having the revolute joints. With the point load at the end point, and we have the frames attached to the end points. Now this is x1, this is y1. I am going to define what is frame x0, y0, frame xi, yi, and this is w1 of x. I am going to define each and every point. Let me make it all the variables associated with this schematic. This is theta 1, that is the frame attached here, and we have the that the frames are finished now. So let me define this as the angle theta 2, and you can say this point, for example, this is the vector which is given by w2 of x2. So now we have the frames associated with the schematic of a 2-link planar flexible manipulator. The frames associated here are, first we have the frame x0, y0, which is basically base frame for the system. Both the robotic system with the rigid link as well as the flexible link will have a base frame, which is the general rule. We have the base frame attached to the base of the manipulator, and we have the frames x1, y1 and x2, y2 and frame x3, y3. So, if you see x1, y1 are connecting the link L1, and then we see x2, y2 and x3, y3 are the frames which are connecting link L2. As you can observe from this schematic, this is link L1's flexibility and this is link L2's flexible link. Configuration is shown here. So, I repeat, the base frame is x0, y0 and the frames associated to link L1 of the flexible manipulator is or x1, y1 and x2, y2, and the frames associated with flexible link L2 or x2, y2, this frame, and x3, y3, which is the end frame. So, each link has the base frame, that is a starting frame, and the end frame attached. So, now go further, that is we say that the rigid motion of this manipulator is described by theta I, with its joint angle theta I, and the transversal deflection of link I is given by Wi of xi, which is the transversal deflection of link I. So, we have two links which is going to be W1 of x1 and W2 of x2. x1 x2 will be varying in such a way that is each xi will vary from 0 to the link length Li. Now coming to the point, let p, that is basically small p, pi with respect to I of xi. See how I define pi with respect to I. That means pi is a point, it is defined in the frame I. That is what it means, pi suffix then superscript. Okay. So pi with respect to I of xi is given by xi wi of xi. So this is a vector, column vector, where xi is the xi value, which is the function of this variable, because we are going to vary this vector by the input argument xi, and wi of xi is the deflection. So the point or the position vector pi with respect to I of xi is given by xi wi of xi. B, the position of a point along the deflected link I with respect to frame xi comma yi, with respect to frame xi comma yi. Therefore, pi be the position of this point or the vector, be the position of this point, of the same point I can say, defined in the base frame. That is it. Now we can have one more notation of a vector, which is Ri plus 1 with respect to I be p I with respect to I of Li, which is nothing but position of origin of frame xi plus 1 comma yi plus 1 with respect to frame xi comma yi, and I plus 1 is position of this point, this frame's origin defined in the base frame. So now we see that the joint rotation matrix corresponding to the rigid link is given by Ri, which is basically the joint rotation matrix corresponding to the rigid link is given by Ri is equal to cos theta I minus sin theta I, sin theta I and cos theta I. Likewise, the rotation matrix EI of the flexible link at the end point is given by EI is equal to 1 minus WIE prime WIE prime 1, where WIE prime is equal to dou WI by dou xi, I mean partial derivative of the expression WI with respect to xi, and we know that xi is a point along the link length, that is what xi. It is in our freedom that we can increment xi by whatever decimal point we can increment, that is in our freedom, and therefore the above absolute position vectors can be expressed as, in general the position vectors can be expressed as p small p I is equal to R I plus W I p I with respect to I. Now, here the W I is a capital W, you can notice that. Now, we have also R I plus 1 getting defined as, in terms of R I, is R I plus W I or I plus 1 with respect to I. You can see that these things 1 and 2 can be cancelled. So, it will be R I plus 1 in the left hand side. So, where W I is the global transformation matrix from the base frame x naught y naught to the frame xi yi, defined by the recursive equation given by W I equal to W I minus 1 E I minus 1 or I, which implies W I minus 1 hat or I with the condition W 0 hat equal to the identity matrix. On the basis of the above equations, the kinematics of any point along the manipulator is completely specified as a function of a joint angle and link deflection W I of x. Thus, the point on the deflected link can be defined with respect to a joint angle theta and the link deflection W I of x. Now, by the assumed modes technique, a finite dimensional model of, say, an order m I of link flexibility can be obtained. That is, by assumed modes method, we can define a finite dimensional model or of the link flexibility. Thus, by the Euler-Bernoulli equation for flexible beams, we have E I phi 2 power 4 W I of x I comma t by dou x I power 4 plus rho I dou square W I of x I comma t by dou t square, which is equal to 0. Thus, by utilizing or exploiting the separability in time and space of the solutions to the Euler-Bernoulli equation, we have, which is coming out to be the link deflection from the solutions of the Euler-Bernoulli equation. We have the link deflection given by W I of x I comma t, which is equal to summation over j equal to 1 to m I W capital W I j of x I multiplied by t I j of t, where rho I is the uniform density and E I with respect to I is the constant flexural rigidity of link I. And here from this equation of link deflection, which is given in terms of W I of x I comma t, we have T I j of t is a time varying variable associated with assumed spatial mode shapes. W I j of x of link I. Now, the definition or the expression for these time varying variables are given by t of t, for example, t of t time varying function is given by a cos omega n t plus b sin omega n t, where omega n is the natural frequency of the beam, which is computed by W n equal to beta n square root of E I by rho. That is the thing. And we have from the boundary conditions, for the flexible link Li, we have W I of 0 comma t, initially it is 0 and W I derivative is also 0 and W I of L I comma t is 0 and W I of double prime L I comma t is equal to 0. With these boundary conditions, we can have the general solution, that is for the first normal mode has the form W I j of x is equal to C n into sin of beta n x. That is for the situation which is pinned. If the first link is pinned, then we have the expression for W I j of x, that is the deflection part is given by C n multiplied by sin of beta n x, and the second link is given by W I j of x equal to C n sin beta n x plus eta n sin hyperbolic of beta n x. So, this is for the first solution is for the pinned situation of the link, and this one, the second solution is for pinned free boundary conditions, where eta n is given by sin beta n L divided by sin hyperbolic beta n L, which implies beta 1 equal to 3.92 divided by L, beta 2 equal to 7.06 by L, and beta 3 equal to 10.21 by L, and beta 4 equal to 13.35 by L. As we consider number of modes here as 4. So, what is modes? So, what modes will do? If mode is 1, the flexible link will have the flexibility like this, say for example. If the mode is 4, we have more flexibility of the link. This is what the difference between modes. If you have more modes, we have more flexibility of the concerned link. If you have single mode, we have the flexibility being reduced. Now, we come to the derivation of forward kinematics of the flexible link. Say the forward kinematics is given by P is a function of theta, joint variable of the rigid link, and the flexibility of the link. So, the absolute linear velocity is given by P dot Pi dot equal to R I dot plus W I dot P I plus W I P I velocity with, because this expression is given already. So, with R I plus 1 I dot equal to P I dot of L I. Okay. So, we can take that W I dot equal to W I minus 1 hat dot R I plus W I minus 1 hat R I dot with W I hat dot equal to W I dot E I plus W I E I dot. So, it has been noted that R I dot equal to S R I theta I dot and E I dot equal to S W I E dot tilde with S being the skew symmetric matrix given by 0 minus 1 1 0. Thus, the tip velocity can be expressed as P dot equal to J theta into theta comma delta into theta dot plus J delta into theta comma delta into delta dot. So, this is the expression. Now, we see quickly the 2 link manipulator flexible ones expression, that is the definition. So, this previous velocity expression is given by considering the vector P I with respect to I of x I being the position of a point along the deflected link L I, which is given by x I W I of x I transpose. So, with this we have the P I also, which is the definition of that point defined in the base frame. So, from this we have derived the velocity and the, that is the velocity in terms of Jacobian for the flexible link. Okay. So, now here P I is position of the same point with respect to the base origin. So, now after defining this, we can go for a planar link, that is a planar 2 link flexible manipulator, where the P I definition for P I is given by P I equal to R I plus W I, put capital W I P I with respect to I, and R I plus 1 is equal to R I plus W I or I plus 1 defined in R I. Here W I is given by W I minus 1 E I minus 1 R I, which implies W hat I minus 1 or I, where W 0 hat is identity. Now, we consider the case I equal to 1. Therefore, P1 is equal to R1, P1 equal to R1 plus W1 P1 1, which implies P1 equal to R1 is basically the origin defined in the base frame is the origin, which is a 0 vector, plus W1 P1 defined in 1. So, here W1 equal to W naught hat R1, which implies identity multiplied by R1. So, basically it is R1. So, W1 is R1, and hence P1 vector is finally obtained to be R1 multiplied by P1 dash, P1 with respect to 1. Now, I equal to 2, where the second frame comes, we have the vector P2 is equal to R2 plus W2 multiplied by the vector R3 defined with respect to frame 2. So, W2 is given by W1 E1 multiplied by the rigidity matrix R2 having the joint variable theta 2. Therefore, W2 is given by W1 hat R2. Finally, R3 is given by R2 plus R1, R2 defined with respect to 1. So, having defined, we have the vector coming out to be P2 is equal to R1 R2 defined in 1 plus R1 E1 R2 P2 defined in 2, which can be written as R1 R2 1 plus R1 E1 and R2 R3 defined in R2, where R3 defined in 2 is given by L2 W of L2, that is at this x, say x equal to the end of the link length L2, the deflection is W of L2. Similarly, R2 defined in 1 is given by L1 W of L1. Thus, finally, we have the position vectors. Thus, having defined the two link planar manipulator of the flexible link with the kinematics defined, now we have the simulation obtained with this type of flexibility of the links L1 and L2 coming out with the traced trajectory of link 1 and the traced trajectory of the link 2, which is basically the tip of this two link planar flexible manipulator trajectory is shown here with its own flexibility. Link 1 shown in the black colored trajectory of the link, and the blue one shows the link 2, flexible link 2, and the tip trajectory is shown by the red trajectory, which is basically the trajectory traced based on the flexibility of the planar manipulator. Finally, we come to the conclusion such a way that in this lecture we have seen the kinematics of the flexible link, basically the modeling up to the Jacobian matrix, and then we have the planar two link manipulator which is flexible, and that example has been derived to get the tip position. And what is needed for this study further is dynamics must be considered for this study, because we have seen in this lecture only the kinematics. Studying about the dynamics will give a more broader view about the theory behind flexibility of manipulators, and then we have seen in the study only the tool, that is a planar motion of the flexible manipulator, but the more generalized way will be studying the 3D flexibility, so that we can have the general homogeneous transformation matrix between the frame I minus 1 and I for a flexible link connecting the frames I minus 1 and I, so that we can have a generalized homogeneous transformation matrix having the flexibility which is delta. So, in terms of delta I, we can have the generalized homogeneous matrix defining the flexibility between two frames connecting the link. Thank you so much.